They will answer a simple but important question. Given an input x, when does the model predict class 1 and when does it predict class 0? Logistic regression begins with a linear score, z is equal to theta transpose x. Then it converts this score into a probability using the sigmoid function. Probability of y equal to 1 given x is equal to sigmoid of z, which is equal to sigmoid function applied to theta transpose x. This is important. The model output is a probability, not a class label. To convert probability into a class label, we choose a threshold t. The standard choice is t equal to zero point 0.5. We predict class 1 if probability is at least t. So thresholding is not the probabilistic model itself. Thresholding is what we do after the model gives us a probability. Now let's derive the decision boundary. Case A, let us start with the most common threshold, that is t equal to zero point 0.5. We predict the class 1 if probability of y equal to 1 given x is greater than or equal to zero point 0.5. That is, sigmoid of theta transpose x is greater than or equal to 0.5. Now we use a key fact about the sigmoid. The sigmoid equals zero point 0.5 exactly when its input is 0. And the sigmoid is an increasing function. So sigmoid is greater than equal to zero point 0.5 exactly when the input is greater than or equal to 0. So with the threshold zero point 0.5, the rule becomes predict class 1 if theta transpose x is greater than or equal to 0. So therefore the decision boundary is where the score is exactly 0. That is theta transpose x equal to 0. Now case B, let's think of a general threshold t. If we choose a threshold t in general, we predict class 1 when sigmoid of theta transpose x is greater than or equal to t. Now applying the inverse of sigmoid, which is the log odds or the logit function, this gives us theta transpose x should be greater than or equal to log of t upon 1 minus t. So let us do a complete numerical example with one feature. Let us choose the parameters theta 0 equal to minus 4 and theta 1 equal to 1. So therefore z is equal to theta 0 into x0, which is considered as 1, and theta 1 into x1, which is minus 4 plus x is equal to x minus 4. Okay, here I am saying x1 and x are the same. When we are converting it into matrix form, basically we create a dummy x0 so that all the thetas have a corresponding x multiplier. So let's consider t equal to zero point 0.5. For threshold zero point 0.5, the boundary is z is equal to 0. That means x minus 4 equal to 0, therefore x equal to 4. Now let us compute the probability at three values. Let's say if x equal to 2, then z equal to minus 2. So probability equal to sigmoid of minus 2, which is 1 upon 1 plus e raised to minus of minus 2. So which is approximately 0.119. This is below 0.5, so it is class 0. X equal to 4, then z is equal to 0. So probability is 0.5. This point lies exactly on the boundary. Let's consider the third point x equal to 6. If x equal to 6, then z is equal to x minus 4, which is 2. So p is equal to sigmoid of 2, which is 1 upon 1 plus e raised to minus 2. It is approximately 0.881. This is above zero point 0.5. So therefore, we'll classify it as class 1. Now let's change the threshold to see how the boundary changes. So let us change the threshold to 0.3. So the boundary condition is z is greater than equal to log of t upon 1 minus t, which is zero point 0.3 upon 1 minus 0.3. So this is log 0.3 upon 0.7 is approximately minus 0.847. But z is equal to x minus 4. So boundary is x minus 4 is equal to minus 0.847. So therefore, x is approximately 3.153. So lowering the threshold has moved the boundary left. Earlier, the boundary was at x equal to 4. Now it has moved left, that is lower, that is x equal to approximately 3.153. So more points will be classified as class 1. So this usually increases the recall and reduces precision. And this connects directly to the precision recall videos that we have already seen.